Okay, this question is for D4 of your moments notes. Okay, let's read. A non-uniform steel rod. Non-uniform, it means that the CG is not in the center. Okay, only when it's uniform, then the CG will be in the center. So it will be somewhere here. Okay, where the weight acts. Okay, the length is 1.8 meters, is balanced, means later we can apply principle of moments. Okay, on top of two electronic balances as shown in diagram below, at X, there is actually a downward force of 0.24 multiplied by 10, because this is the mass reading on the electronic balance. So using W equals to mg, I take 0.24, and if this is happening on Earth, then it will be 2.4 Newton. Okay, that means this rod is pressing down on the electronic balance, meaning the electronic balance is also applying a force of Fx upwards to support this steel rod. Similarly for Y, there is a force Y that is supporting the steel rod, and the value it is W equals to mg again, 0.26 multiplied by 10, I should get a value of 2.6 Newton. Okay, now the total upward force is 2.4 plus 2.6. It must be equals to weight. Therefore, the weight must be 2.4 plus 2.6 Newton. Right? It will not be more, it will not be less. It must just be equal to the total upward force. So 5 Newton. Alright, so they want us to find the distance of the center of gravity. So they want us to actually find this distance, the perpendicular distance. Alright, so we can either, this is clearly a two pivot question. We can assign the pivot at either X or Y. But take note, if I assign the pivot at X, Fx perpendicular distance will be 0. Right? If I were to assign the pivot at X and I draw the line of action of Fx, it will pass through the pivot, meaning the perpendicular distance will be 0. Means later it will not appear in the formula. But if I choose Y as the pivot, okay, and again drawing the line of action of Y, force Y, it passes through the pivot. If the pivot is assigned to be at Y, then the perpendicular distance will be 0, meaning there will be no moment due to force Y. Okay, but since they want us to find the distance of the weight of the CG to NX, which is this distance marked out by me, then I will let the pivot to be at X. So I will erase the pivot at Y. Okay, so take pivot at X. So this is my first step, right? Remember the sixth step. Second, I will identify how many forces. So there are three forces: Fx, W, and Fy. Fx happens to be 2.4, W is 5, Fy is 2.6. Alright. Step 3, perpendicular distance. Okay, so because the pivot is at X, the perpendicular distance of the line of action of Fx is 0. So I put a bracket 0 here. For weight, it is D. For Fy, it is the entire length of the rod, so it's 1.8. Okay, so step 3 is finding perpendicular distance. Step 4, moment equals to force times perpendicular distance. So if I were to take 2.4 multiplied by 0, you will get 0. So the moment of X is 0. Moment of the weight equals to 5 times D. So it is 5D. Okay. Moment of F due to force Y, moment Y equals to 2.6 times 1.8. So equals to 4.68. Okay. So that is step 4, multiplying the force and the perpendicular distance to find the moment due to each force. Step 5, finding direction. Is it clockwise or anti-clockwise? Because this mx is 0, so no need to find its direction. For mw, which is the moment due to weight, it is going to be this direction, so it's going to be clockwise. For my, the moment due to force y is going to be anti-clockwise. Okay, we just did, I just explained using how to use the pen to find the direction. Step 6, we can apply principle of moment, which is sum of clockwise equals to sum of anti-clockwise. So 5d equals to 4.68. Therefore, d will be 0.936 meters. Okay, so you can try out using pivot at y, after that using 1.8 to minus that distance. Okay, if I were to use another alternative method, some students may want to put pivot at y and then to find this green color d, and then after that you can use 1.8 to minus d to find this distance. Okay, you can try it. Okay, I'm going to continue with success criteria E. Now, show understanding that the weight of a body may be taken as acting at a single point known as its center of gravity. Actually, we have already done that in our calculation. Okay, so when gravity acts on a body, every particle is attracted towards Earth. Total weight of the particles can be represented by a single weight acting on a single point. Alright, so this is the definition for center of gravity. It is defined as an imaginary point through which its entire weight appears to act. So this you need to memorize as the definition. Now, an object can be balanced at its center of gravity because its weight has no moment. Why doesn't it have any moment? Because the perpendicular distance of the line of action of the weight to the pivot is 0, right? Which means the resultant moment is 0. So look at this rod. This rod is actually a uniform rod. If it's a uniform rod, the CG, the center of gravity will be in the center, the geometrical center. So if I were to put a pivot or put a finger below it to be the pivot, the line of action of the force of its weight will be passing through the pivot. So there's no perpendicular distance. If there's no perpendicular distance, no moment, because moment is force times perpendicular distance. If the perpendicular distance is 0, that means there's no moment. Okay, for a regularly shaped uniform object, the center of gravity lies at the geometrical center, right? So you can actually sort of divide it. You can locate it by drawing two perpendicular lines which divide the shape into two equal halves. Okay, but sometimes for a ring, okay, for a ring, the CG will still be in the center even though there's nothing in it. Okay, but if I were to divide it into half, two equal half, then you will find that the CG is in the center. Next point, no matter how an object is placed having different orientations, the weight of the object always acts vertically downwards through the CG. Okay, so in this case, it's the same object, the box here. The CG is in the center. Yes, so no matter how I place the box in different orientation, it always acts vertically downwards. For a non-uniform object, the center of gravity is located nearer to the heavier part. It makes sense, right? So if I were to put a pivot here to balance it, it will not have any turning effect. Okay, there will be no moment. Okay, this lists the steps to find the CG of an irregular laminar. O-level questions came out this as a designing an experiment. Okay, in order to find the CG of irregular laminar. So you read the steps. Basically, you punch 3 holes at the 3 corners. Excuse me. The 3 holes have to be as far apart as possible. Okay, they have to be as far apart. Okay, and then you suspend the laminar hanging freely from a support at 1 hole. Then we hang a plumb line from the same support. Plumb line, basically there is a bob here, and because the weight will always act vertically downwards, it should allow us to draw this vertical line. Then we suspend it at another point, right? So maybe this is the first point, we can suspend it at a second point, and then we are also able to draw the vertical line due to the plumb line. Okay, then the intersection will be the center of gravity. Okay, success criteria F, describe qualitatively the effect of the position of the CG on the stability. Now, what is stability? Please memorize this. The stability refers to a measure of the object, its ability to return to its original position. Okay, when displaced, when it's moved slightly. Okay, now take note, stability of an object depends on the position of the center of gravity and the base area. The lower the CG, the more stable the object is. So imagine a man standing this way, okay, and a man standing this way, right? So the CG is actually drop when he stoop lower. You will see this example in sumo wrestlers. Alright. Next, the greater the base area, the more stable the object is. Okay, so basically this guy is creating a larger base area, so he'll be more stable. Now, if you look at these two bookshelves, A and B, obviously they have the same base area. But because for A, the books are placed higher, the CG is higher. Versus bookshelf B, same kind of books, they are placed at the lower shelf, the CG is lower. So change this to CG. So B is more stable. Okay. Now, if the line of action of the weight falls within the base of an object, so for this is the base. If the weight falls within the base area, the object will be stable. Now, this is what, for scenario B, this is what a lot of boys like to do. They like to balance on their bench. Please don't try this in the lab. Okay, so they try to make their CG pass through one of the bench leg. Okay, and it's quite hard to achieve. So I say again, please do not try this in the lab or even in the classroom. So this is, although it says here it's very stable, but any point in time, like here, your body goes backwards, there will be a toppling moment. Why? Because here is the pivot. And do you see that there is actually a perpendicular distance? For B, it's very hard to achieve because the line of action of the weight actually passes through this very small point, which is the pivot. And any slight movement will cause the weight to fall outside this pivot. And then there will be a toppling moment. Okay, so if you read, the wooden block in orientation B is not or just about to topple over. Okay, as the weight lies vertically above the pivot. So the perpendicular distance from the line of action of the force to the pivot is 0. Therefore, the weight does not have any moment. But this is very difficult to achieve. Okay, don't try this in the lab. Now, the wooden block in orientation C is toppling over because the perpendicular distance of the line of action of the weight to the pivot is not 0. So the keywords are perpendicular distance of the line of action of the force or weight, okay, to the pivot. You need to always have this in your explanation questions. Okay, therefore, the weight produces a clockwise moment about the pivot, and then the block, which is looking like this, will topple. Okay, you can try F1 and then you refer back to the answer in the video. Okay, I hope you have tried F1 before you look at the second part of this video. Now, figure 1 shows a sheet of metal suspended from a hole in one corner at A. The weight of the metal is 0.1 Newton. Okay, so this is the weight, and the center of gravity is at B. Okay, so these are the things that we take note. Diagram is drawn full scale. Okay, what I have done here may not be what is in your paper, because for here I can zoom in and out. Okay, but your paper is printed, so it's fixed. Okay, so later on, if it's drawn full scale, that means you are able to measure. Now A, the sheet turns because of the moment of the weight about pivot A. So the pivot is here. Okay, state what is meant by moment of a force. Now state what is meant by the moment of a force. This is the definition for moment. Moment of a force is the product of the force and the perpendicular distance of the line of action of the force to the pivot. Sorry. Please memorize. In part 2, using a measurement taken from figure 1, calculate the moment of the weight about point A. On figure 1, indicate the measurement that you will take. Okay, I know some of you will directly be drawing this and measuring it. Okay, this is what I warn you against. Always draw the line of action of the force. Okay, and this is the pivot. So I will be looking at the perpendicular distance, which is this. So what you're measuring should be this value here. Okay, I discovered that sometimes I don't record, so I'm going to backtrack here, yeah. Okay, the sheet in figure 1 swings freely and comes to rest. Okay, why does the sheet swings freely? Okay, because this is the weight, right? The line of action of the force. And you know that there's a perpendicular distance. So this thing is going to be swinging clockwise. But it's not going to directly stop here, right? It will continue swinging past the pivot. So the weight may end up somewhere like here. Okay, the sheet. And then it will swing back anti-clockwise. And the swinging gets lesser and lesser until eventually the weight or the CG lies vertically below the pivot. That's where the perpendicular distance is 0, and that's where there will be no more moment. Okay, so that's why it swings freely and eventually it will come to rest. In the space below, sketch a diagram of the sheet in its final position. Mark A and B. So this is going to be A, this is going to be B. The center of gravity is below, vertically below the pivot. So there's no perpendicular distance. Okay, and this is how we should answer. Explain why the sheet remains at rest in this position. Okay, so why does the sheet remain at rest in this position? In this position, the center of gravity is vertically below the pivot. The line of action of the weight passes through the pivot, and the perpendicular distance of the line of action of the weight from the pivot is 0. Since moment is force times perpendicular distance, therefore the moment is 0. Okay, now the metal sheet is placed on a table. State 2 reasons why it is more stable. So this is got to do with your stability. Okay, when it's placed flat on a table, then when it's placed on a table in a vertical position. So now this is stable, we place it flat. Okay, versus just now when it was placed vertically. So when it's placed flat, what happens to the CG? The CG gets lower. Okay, and also the base area increases, right? The base area is just this tiny area here, but for when I lay it flat, it is the whole area. Alright, so when the CG gets lower and the base area increase, it increases stability. Okay, so I think I'll stop this video. Please look through again if you don't understand. I will upload this video for F2 in a separate video because I don't want this video to be too long.